to the eighth tutorial of reinforcement learning. So today we'll discuss TD policy evaluation. The first part we'll discuss with linear function approximation. And in the second part, we'll implement neural network based TD policy. Neural network is one of the most popularly used function approximation tool, which is non-linear. But the theory we'll discuss in light of linear function approximation. So when we talk about policy evaluation, we have a policy fixed. So say the policy is pi. We will evaluate p pi policy. Is obvious. And have MDP. So we'll discuss this in context of discounted MDP. Have a statements. This action space. Transition probability unknown, reward function, and discount factor down. So you know that V pi satisfies the Bellman equation, which is basically V pi S to R is A. Over next state, this time probability that at current state, after taking action according to the policy pi, will end up in state S prime, and then multiply V pi S prime. And here there is a discount factor, so multiply gamma here. So this is what the Bellman equation is. And for function approximation, we approximate this V pi with some approximation class. So which is as follows. Function approximation for V pi. Consider a class of functions.
So it should not be R of SA, no, in case of V5. It should be
Oh,
just be
yes,
R of S.
is pi s. Instead of a, it will be pi s. Now you can consider, of course, randomized policy. Uh, but here
Uh-huh.
I'm considering deterministic. So, uh, yeah, coming back to the discussion, how V pi is approximated. So we consider a class of function which is parameterized. What do I mean by that? So class of functions use this calligraphy capital F for that class of functions. F of theta, where theta belongs to a set capital theta. For example, so okay, let me also write the domain and range of the function. F is a function from state space to real, such that theta belongs to uh, capital theta. So capital theta is a say X. Take an example. The capital theta is from 0 to 1, 2 dimension. So this is so this region is capital theta, and say the class of function that is parameter when it is parameterized by theta, that is defined as follows: f x, how should I write this is a function of states. If s theta is s1 theta 1 plus s2 theta 2 plus say some c. C is a constant. For every theta, c is not changing. So
So this
this is a
theta belonging to interval 0 and 1, is this done for theoretical convenience or well, to prove the theory behind it, or it is the norm of implementation?
no. There is okay. One thing is if your theta is from some compact space, that might give you some advantage. But the uh, point here is okay. If theta is some unbounded set, there could be instability. I mean, theta. So after all, you will optimize your there will be some optimization problem running in the after some point of time. You will optimize some objective function. Right? So you will do something like gradient descent, stochastic gradient descent. Uh,
Okay.
when you do that gradient descent, it could happen that for some set of data, your theta will grow very large. So it's a good idea to have a compact set of parameters.
But
But
let's say when you do that LSTD and you do A inverse B, what happens when that A inverse B leads to theta outside of this range?
okay, so I think there is no restriction on theta there, right? As far I can
There is no
remember.
restriction, at least in the to class videos, they did not
Yes.
give any restriction on theta over there in
Okay.
LSTD.
Fine. So here the restriction I put just to like for the sake of given example, we can consider also R2. I mean, instead of this, we can also consider entire rail line of
Okay,
uh,
okay, okay. Just
Euclidean
wondering
space.
whether when we go for real implementation, is this how it is done usually?
Okay. Uh, yeah, so if there is no stability issues, then I think we can go with the entire space.
Okay, okay.
Okay, so this is an example of how parameterization is done. So here I am also considering this S is in S, the state space is also two-dimensional. So there is S1 and S2. Okay, so yeah, that's what it is. And then
This is the parameterization of V of S, no? So this
yes,
F of
so
S, this is actually we are approximating V of S.
yes, V pi. Yeah,
Yeah, okay, V pi, okay. Yeah, good.
yes. So here are some notations I'm writing. So this is an MDP, right? And when I am fixing a policy, then we have for fixed policy, we have a Markov chain, induced Markov chain, and Markov chain has a transition matrix. So for this case, when we are fixing the policy pi, let us denote the transition matrix of the induced Markov chain by p pi. So p pi is so used and uh, for Markov chains, the Markov chain converges to, I mean, it's not true always, but if some properties which is called ergodicity property, if ergodicity property is satisfied, then the state distribution of the Markov chain converges to uh, something called stationary distribution. So we denote that by d pi, stationary distribution d pi. So d pi is vector, d pi is a vector, d pi is a matrix. So this d pi and t pi satisfy this following equation, d pi times. So d pi consider it as uh, row vector, as p pi is equals to d pi, this equation. And let's say phi, capital P, this is feature matrix. So now I'm talking about uh, linear function summation. So there will be feature matrix.
One question over here is if the problem itself is of non-stationary nature, this method will still work.
Non-stationary as
So here your d pi, you are assuming a stationary distribution, which means the nature of the problem itself is stationary, right?
okay. So here is what I mean by stationary distribution is uh, just a second. Okay. So yes,
So,
here the process is definitely stationary. That means the Markov chain has, when I'm fixing a policy, uh, the transition matrix is like p pi is true for, so what is p pi? P pi uh, ij, that is ith row and jth column. This means the probability that st plus 1 is j, given st is I. This is the probability, and this is true for all t. Okay.
So, so yeah, so all T, okay, okay.
Yes.
Uh,
So yes. So this is stationary uh, process, and
but it is still the method is still applicable for non-stationary processes.
no, it's not. When we talk about infinite horizon problems, the I mean, whatever we discuss is mostly stationary. Uh, and at least in this course, we do not talk about non-stationarity if the process or the problem is infinite horizon problem.
Okay, okay,
And
okay.
yeah, there are works on non-stationarity, but they assume that there is a process which, I mean, the process deviates slightly from a stationary process in the long run.
Okay, okay. And if you keep repeating this method over and over and over, like in control problem, let's say you have this explore exploit choice going on, then eventually it will catch up to the non-stationarity, is it? So let's say I am running, so I am driving a car. Let's say I'm teaching the algorithm to drive a car, right? And I have taught it to drive it in 5 cities, right? And when I go
Yes.
to deploy the same algorithm in the sixth city, which I have not trained, that assumes that the distribution itself has undergone a transition, right? The
Yes.
environment itself has.
Yes. Yeah, I think I understood your question. So, for every algorithm, you need some time to uh, learn, right? So, say for this TD policy evaluation, or say Q learning, you're applying Q learning, and say you have your algorithm works if you gather, say, 1 million samples. So you need some time. If you are coming to the new environment, you need, in that new environment, you need 1 million samples. After that, your algorithm starts performing like uh, like what you expect to do from the algorithm. Now, if the environment changes before that, then there is no point, right?
But then how would I apply this in a live setting? So
Yeah.
let's
So
say I
first,
want the learning to happen all the time,
yeah.
like in a
So
control
it's
setting.
Yeah, right. So it's I mean, it's a still open question, and like if uh, if your algorithm cannot run fast, then it's not very uh, I mean, not very useful in non-stationary setting. That's true. And there is
Okay.
one
Okay,
line.
I'll give you a simple example. Let's say I have developed a person detector, right? Person detector on a thermal camera. Let's say
Yes.
just so thermal camera gives a temperature. So usually what happens with the person detection is it will also learn kind of the environment along with the actual object. Usually with neural networks, it does like kind of overfit to the environment. Now let's say I have made it. I have some samples drawn from Maharashtra, Bengal, and whatnot, and then suddenly my like my application is in Jammu and Kashmir, right?
Yes.
So now I want that person detector to perform in Jammu and Kashmir. I know that it won't perform straight away, but I want to use this technique, let's say reinforcement learning technique, without having to manually intervene. है ना? So let's say assume that the feedback will come from the operators, whoever is working over in, we'll get some kind of a reward like feedback where the when the algorithm makes a mistake, they press a button or that kind of stuff. Right? Let's just assume that there is a feedback available of a reward at this stage. So then I want to apply, let's say, this method in that scenario. How will that work out?
Okay, so I mean, for if that's what I'm trying to say, for every algorithm, there is a sample complexity. That is how many samples you can. So uh, there is something called sim to real transform. So this is similar to that. Sim to real means you have trained your algorithm with some samples in simulation, and then you transferring the algorithm to the uh, real environment. So in simulation, you cannot always simulate the uh, exact environment which is in their the real life. So you start with when you transfer to the real life, you start with a like decent enough policy, so that you
Uh,
need much lesser samples to learn it in the real life.
okay,
So
okay, got
yeah,
it, got
so
it.
so all these things comes under the theory of sample complexity. So
Okay,
uh,
okay, got
you
it.
can
Sorry for interrupting. I just like
yeah. And what I was going to tell is for there is something called change point detection. So if you're so there is a set of algorithms. Say you are controlling a linear system, and so if you know, I don't know, this linear system has two matrices, A and B. So
uh,
xt plus 1 equals to axt plus but plus some noise. So
mm,
it can happen that for your system, this A and B metrics, which are basically the environment, so
mm,
they may change over time. So
mm.
there are some algorithms like which detects when it changes and then restart your estimation part of the algorithm. So it say
Okay,
the
okay.
algorithm estimates A and B. Yeah, so all of these things are done in theory, but I mean, still we are far away from implementing in real life.
Got it, got it. Good, thanks.
Okay, so here this is the transition matrix, and as I have said that d pi is a distribution which satisfy this equation. So what does it mean? It means that from wherever you start your process, uh, limit t tends to infinity, probability that your state at time t st is equals to s. That thing converges to d by s. So yeah, that's what it means physically, physical significance of d pi. And given this function approximation, we try to minimize an error. That is what this LSTD is explained.
Your page is not changing if you're writing something.
Oh, is it?
Yeah, it's stuck at that p pi ij which you wrote. No? It's stuck on that line.
Yeah, but I am,
This this part was not. Now it is. Now it is okay.
there is some lag. I think it is because the internet. Okay, so so our goal is to minimize parameter. Let's in the lectures, I think W is used for parameters instead. So, right.
Yeah, I think W was that weight matrix for d pi. I think
Wait, okay, what is the parameter?
Yeah, no, parameter was theta only. Uh,
Oh, okay,
yeah,
fine.
yeah.
Okay, so we minimize for parameters. So feature is function of states. Step. So this is what linear function approximation is. So this we are finding the best theta, which minimizes this. So what does it mean physically? You say this theta is this plane.
Yeah, you're just trying to represent. You're trying to parameterize that state actually. Best finding the best parameter. Uh,
Yes.
Basically
So
reducing the dimensionality in some sense from a lookup table.
yes. This is the theta space, and uh, your v pi necessarily not lie in. Uh, so this is the space of uh, functions. So this I think I should write like this. I think I should write if, which is basically all phi plus is in the parameter space. So this plane represent all the functions that we can parameterize. We are sort of trying to find the best function. Uh, say this is v pi, and we are trying to bring a trying to find a closest point on this function plus. So this is zero. So all these are in function space. Okay. Then what does v pi this d pi is doing? D pi is in a sense d pi is distorting the space into like transforming the space. Uh, sort of I had an image of this. Find it.
I get the idea. Like you're saying VPI is some higher dimensional space in reality, but you are trying to approximate it with a planar kind of lower dimensional planar structure,
Yes,
where
true.
it still captures the essence of the problem.
Yes, true. And then what I'm saying is this what this d pi is doing. So d pi is if you let me write it in matrix notation. So this will be in matrix notation. It will be and write this as so v pi is the vector. Uh, v pi is instead of function you can think it as a vector, and then pw p theta. So p theta this P is a matrix and theta is a vector. So P theta is also P theta is a vector which is approximating V pi. So this objective we can write as half times d pi minus P transpose. Then d pi again consider it okay, not vector, but let's construct this matrix D capital D pi and write in what it is. Then P pi minus P theta. So V pi is a matrix of size S cross 1, cardinality of S cross 1. Then there is a matrix P, which is so the feature space has some dimension. Let's call it D. So S phi is of dimension S cross D, and theta is the feature of the same dimension as D cross 1. Theta will have element equals to number of features. And this is the first one. So entire thing is now S cross 1. So what is D pi? D pi is a matrix which is diagonal matrix. So all the other elements are, other than diagonal, all are 0. And the diagonal elements is the vector d pi. That is, first element will be d pi of 1 and last element will be d pi of s. So you can check that this is exactly equals to d pi s. Minus phi s theta is transpose theta. So these two things are same. So what it's doing is it's some way it's distorting the space with so uh, in Euclidean space x minus y 2 is basically x minus y transpose x transpose x minus y. So this is called L2 norm. And similarly, we can also write induced norm, which is defined as x minus y p d x minus y. So this is called induced. Or I think I forgot the exact term. Probably it is not called induced term.
This is also like Mahalanobis distance, no?
I'm not sure. So that was probably,
So I think,
I'm not sure.
but this is like there are zeros on both sides, so it is a diagonal. In Mahalanobis, there is also a relative. So it's not a diagonal matrix. It is a full covariance matrix where
No,
there is
no.
correlation
So
between the dimensions.
no. So D. I'm not saying that D has certain properties. I mean, it has to be PSD. But what I'm saying is, uh, sorry, it has to be positive definite. I'm not saying that D is some covariance matrix or this is any matrix which is positive definite. And what I'm saying is this is a new type of metric in that space. It's not exactly L2 metric, right? So
Okay, so as zero is necessary, yeah? Or there could be uh,
Zero is
that it's necessarily a diagonal matrix, is it?
no, D is not need not to be a diagonal matrix. For
There could
this
there
example,
could be
it's
core. Okay, got it. But there could be correlation, no, between dimensions. So not necessarily a diagonal matrix.
so yeah, don't think it as the correlation. I mean, covariance matrix or anything. It can be any matrix, any deterministic thing. So I mean,
Okay, okay,
anything.
okay, okay. Cool.
Okay, so so how did we do this TD learning? So there we had we had yes, what to use T. Um, we had of this T. I'm not writing T dependence here. So this is equals to we have this T plus some alpha T T by T plus T plus 1 minus what you had earlier. So this is just to remember that what TD learning is. Now we want to minimize this function, right? So if you minimize, if you want to minimize a function, so the function be theta. Are you seeing the screen to move?
I think there is some issue with my internet, so it could be my internet also. Which is I'm
Uh,
getting slow updates actually.
so to solve this, we can apply gradient descent, short GT. So how does that go? Theta n plus 1 is updated as theta n. So this is we are minimizing. So we take step in the negative direction of the gradient, beta t, step size, and then gradient of p theta. So if we consider this e theta to be this objective, then what will be the gradient? So for minimize theta half p pi p theta constitutes p by p pi minus p theta. So if we minimize that, I mean, if we take the gradient of this objective, then we'll get in d pi minus gradient of d. Okay, I may do some mistake. So let me just expand this and then do the calculation of d pi transpose d pi minus. Now it's easier. So minus d pi transpose d pi d plus okay, so you know that if we equate the gradient to zero, then we'll get the optimal point, right? So let's find what is the optimal point. So the optimal point here will be uh, hope I have done right calculation. Okay, but this we cannot solve for sure because we do not know d pi. By this we got by equating gradient of e theta to zero, but this is impossible to solve. Because of v pi and d. So v pi is what exactly we are trying to evaluate, and in the process, if we have v pi, that makes no sense. So okay, now going back to the gradient descent update, let's write what should that look like. Theta n plus one equals to theta n minus theta n uh, times the gradient. I can see there is a huge lag between this, uh, what I'm writing and this being shown. Okay, so okay, so this is V pi transpose V pi P plus P transpose V pi P theta theta in, right? Okay, so let me write this in slightly different way. I think we can write this, the first term, this we can write P transpose T by V by E, we can take side V transpose from both the equations. Then it will be, what will remain is D, D by also you can take outside. And then it will be P theta N minus V by. So this is what your approximation is. Approximation of V by at nth iteration. And this is your
I can't see a screen
uh,
actually.
your vertical. Okay, I'm
I don't know.
unsharing and resharing. Can you hear me now?
I can hear you, but I can't see the screen.
Yeah, I'm unsharing. Is it visible now?
No, not yet. I don't know if it's a problem with my internet or
No, I think
something at
it's
your end.
on my end as well.
Maybe we can restart the meeting.
That will create some problem because I have to upload this video in video. Let
Okay,
me
okay.
take that restart in the last. Is it visible now?
Yes, visible. Yeah, yeah. Visible.
Okay, so what I was saying that so yeah, we have the objective function what we are trying to minimize, and uh, if we do uh, equate the gradient equals to zero, that will give us the optimal parameter. But that is not possible to compute because of reasons uh, v pi and d pi in the equation. So what should we do is we can think about gradient descent. Let me place this in. So you cannot apply the direct method. Let us see if there is any way to apply the gradient descent. And we see that the gradient descent update looks like this, this equation. So there will be a CO. Oh no, yes. So theta n minus theta n, which is the step size, then uh, the feature matrix transpose d pi. Then here the thing is that first one is the approximation of v pi, and second one is the true v pi. Now, true v pi is not possible to compute, so we can take idea from this TD learning here. So TD, what does TD learning do? It replaces the target with this. So once you have sample, we replace this. So this was supposed to be V pi S T, but instead of V pi S T, we approximate is it by R S P A T plus gamma V at S T plus 1. So the same idea we can use here as well. So uh, let me write modification 1. Eliminate V pi. So for that, what we can do is theta n plus 1 equals to theta n minus theta n P transpose P pi P theta n. I think again
Yeah,
the
yeah. It's stuck.
connection is not.
That screen is stuck on modification.
Your way is connection is so bad. I think it has moved now. So minus, what we can do is, okay, the first modification has to be eliminate the expectation. So, or eliminate expectation, or let me write sample version. What does it mean? That is, every time you update it, you have to take this expectation, right? D by S. So you do not know D by, and then for every S you have to update this. So that is not possible because we are collecting samples and then doing the update. So what we rather do is we update this theta n plus 1, theta n minus beta n. So look at the state at uh, time n is in. Okay, so okay, so far we are denoting time by t. How? Let's write as saying theta transpose is n. Eliminate d pi because now we are only considering the.
You can actually turn off your video and see if that helps
Okay,
because the screen is
but
again stuck.
okay, but I think this is the problem of connectivity from the
Yeah,
pad.
yeah. But if you okay, okay. But your video seems to be continuous, just that the slides are not up modified. So at least it may save some bandwidth.
So this way we are eliminating the expectation, and then we, instead of the transpose, we can write p then, and so this inside whatever is there is a scalar. But now modification two. So when you change your gradient descent to a sample version, what do you call it? We call it stochastic gradient. So this is exactly what SGD is. We do not take the expectation, rather we work with samples. Modification to eliminate phi by. So instead of v pi, we replace v pi with a moving target based on your current next sample. Minus, we have collected some reward r in plus gamma times p transpose is n plus 1 theta n. So this is now your moving target. So this is what the algorithm is. And
So here the phi transpose S of n is a vector. Is it?
yes, P transpose S of n is a vector of dimension d plus 1. D is the dimension of the feature vectors.
D plus
So,
one. Okay, okay. Phi
so
transpose. Okay.
this entire thing inside the bracket belongs to R. This is the real number.
Okay,
And
okay. And
this
you
one is in RD.
RD. And basically, every time you make you pull the arms, you change the Sn is the state at that time n, right? And you make this update at every arm pull kind of thing.
Okay. So every time you take an action and we'll get a new state and reward, you can update the theta.
Okay, okay. Okay. Got it.
Well, so this is the linear version, and you can show that. So here we have got a optimal theta, right? So here we got some theta opt. You can show if some conditions are satisfied, then this theta n converges to some theta star, that limit n tends to infinity, theta n plus certain theta n converges to theta star, then theta star minus theta opt. They are bounded above by some parameters of the problem. So this is how. Well, now let me write the general function approximation version of this TD learning, which is, of course, very similar to this. So uh, phi theta, instead of phi theta, we have we approximate phi theta is replaced by if. Now phi theta is of course one type of f theta, but here we have no linearity restriction on the function class. So here how the algorithm will look like. So what will be the objective? The theta of p pi minus f p pi. Then gradient of theta p. So if we can, I mean, it's a function, but we can think like a vector, right? Minus if theta transpose d pi p plus hope I am writing it correctly. So this is S plus S. This is one. This is D. And some mistake. So
So wherever you have in the linear part, theta, right?
yes,
We can just replace that with gradient of f of theta. No?
yes, but thing is, here I got theta, that's right. But here I had phi theta, so phi was there, and
Like phi was there, sorry, not theta. So instead of there will be
gradient
just gradient
of,
of
sorry, I think we could gradient of f. Oh, so what did we see? Phi, think this is what I should be. I'm not very conscious what I'm doing.
This is what it will be in case of a neural network, no, where X is a neural network.
Yes,
Okay, can you explain like in a practical scenario? Let's say you have a neural network which represents your function from theta to Vs, right? And you draw a sample, right? Then what do you do?
okay. Let's avoid this discussion here, and I'll get back to this again.
Hmm.
Okay, so you're talking about the practical implementations.
Yeah, about neural network. Let's say that f of theta is a neural network now. Theta is the weight,
Yes,
and yeah, you are getting some kind of a fully connected network to go from theta to Vs, right?
yes.
How practical? So let's say you draw a sample, then what do you do?
Yeah, so there are two ways. One, you are drawing the samples and updating your theta. That's that's what this relearning, this algorithm, at least this algorithm is suggesting.
But
Right.
first, so you basically
But
so you treat so when you draw a sample, essentially you drew a stochastic gradient descent on the neural network, is it? With a single sample.
yes, so I mean, if uh, one way is to look at it is you keep collecting samples, and at ST you are collecting ST, AT, RT, and ST plus one, and you are updating the your theta T at that time, and then you are discarding that sample. You are not using that anymore further.
Hmm.
But that seems to be a very inefficient approach because uh, I mean, that's still a sample. I mean, you can use that sample to update your theta again, but
Okay.
this approach doesn't do it. So
So
another way
how
is called, yeah, yeah. So another way is called replay buffer.
replay buffer? Okay.
So in DQN that is used mostly, and in DQN literature that time. So you keep on collecting samples. So ST, AT, RT, ST plus one equals to 1 to some capital T. I mean,
Hmm.
in town, you keep on collecting these samples. So this is your data you
Mini
can
batch.
think of. You can think this as your data. And when you are updating your neural network, you can use this following objective: one by number of samples in T.
Okay.
If ST. So here the update of the neural network is like independent of number of samples you are collecting. So here I'm not writing theta T. You're writing some theta N. minus, so this is your value estimate, given your theta n, this is your value estimate uh, for state st, and you whatever you I'll write, that has to be summing from equals to 1 to tau f st theta n minus, you have rt plus you have gamma, and here comes your target f of st plus 1 theta n. So now this is your loss function, and then you take a gradient of this loss function and update your theta n. So we'll have theta n plus 1 then, and that's how
Makes
it
sense.
goes.
Makes sense.
So this is mainly done in DQN, deep Q networks. So this way you are not throwing any samples away.
Okay, okay. So there is also a section in the uh, in this week's videos on LSPI and fitted Q. Can you can you explain a bit of that with LSPI and fitted Q?
Okay, let me check.
It is the last video,
Hmm.
LSPI and fitted Q. Can you explain what that is?
LSPI. Okay. Okay, this I have not gone through. So what I can do is okay. So I
Uh,
have to, yeah,
so
I
that
have,
is, if possible,
yeah,
so if possible, can you just at a very high level, in an intuitive sense, can you just explain that eligibility again? Because he has mixed, the professor has mixed function approximation with eligibility traces, right? So if in
yes,
like in short time you can like give an intuitive understanding of that uh, eligibility, then it will be very nice actually, if possible.
okay. So eligibility trace is where I think in tutorial 5, I guess.
Yeah, yeah, it is there in tutorial 5, but the professor has kind of combined this function approximation with eligibility traces also, right? So if you can like kind
Yes.
of quickly tell me, kind of quickly explain the idea of eligibility traces, it will be more concrete in the head.
Just here. So the idea is as follows. So here you have in TD learning, you have only, can you see the screen?
Yeah, yeah, I can see the screen.
Okay. In TD learning, you have only this
Single state of
lambda
it.
here. So only one state here, only m equals to uh, 0 you have it,
Hmm, hmm,
right?
hmm.
So here instead of this, I mean, you cannot take up to infinity. So aim at to some terms. And here in function approximation, you are replacing these two things with that, I mean, for linear function approximation, phi, uh, theta
True,
and
true, true.
r, or phi theta, sorry,
You're
RT.
just basically you are figuring out there is some function which kind of gives you V pi.
Yes. So instead of doing it for one sample, you are doing it for multiple samples.
Ah,
And here it says Q plus 1.
okay, okay. So in eligibility traces, essentially you do it, you average it across basically it's like GT1, GT2, GT3, GT4, and you take an average across all GTs, is it?
Yes, sort of. I mean, some weighted geometric sum.
Weighted average, and eventually
Yes.
that lambda will make the uh, GTN die out.
Yes.
Okay, 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 okay.
I think professor has presented in some other some ET we defined. It is, I think, this each update, right?
Yeah. So basically, in this lecture also, he has kind of so TD0 and TD lambda he did it in last lecture, and then he has described how that lambda can be introduced into uh, function approximation as well.
Yes, yes. There comes this. I mean, each term is sort of ET, and you update this by multiplying lambda to ET. I mean, something. The iteration is something like this. Something ET plus one. So lambda times ET plus this new term.
Okay, 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 okay.
I
Just
may
lam.
do some mistake, but I think
No, I get the idea. We
this is
basically
how
just
it is.
multiply the previous error by lambda.
Yes, yes.
Okay, okay, okay,
So yeah, that's how you do it. Like yeah,
okay,
I mean incrementally.
okay, okay. Makes sense.
Okay, so I'm not sure whether I should go with this. I think I should fix the theory first and then go with the implementation. Uh, let's erase this thing. The replay buffer will implement, so let's keep this. If we compare this with the DD,
So is this how the only way you basically deploy neural network is to estimate like have a function approximation of the v pi, or there is other ways you do this in neural network?
sorry, I couldn't understand.
So basically, what we are seeing over here is you are using neural networks to do function approximation, right?
Mhm.
And what I was talking to you about initially was to kind of learn the online learning setup, right? So
Yeah,
that
this
is
is yeah,
this is just
okay.
estimating the value
Yes,
state value, sorry, right? And that in that case, you are actually learning the function itself, meaning you are learning. So let me say. So let's say if you
okay.
are dealing. Hmm,
So neural network is a type of function approximation. So
huh.
you know this, right? The neural networks has weights and biases, connections, and all.
Hmm, hmm, hmm,
So say this is a two-layer neural network.
hmm.
So we have all the
So,
connections and all.
no, what I was asking was in my case, so let's say there is object tracking. I'm doing object tracking or object recognition, let's say object recognition.
Yeah.
How would you formulate the problem is what I wanted to ask. So
Okay,
I
so
told you I told you a scenario, no, where let's say I've trained some object detector in particular setting, and then at the customer end, the environment has kind of changed, and I want to use reinforcement learning to do that online learning kind of thing, right? Where I'll assume I have feedback. Uh, if my algorithm, let's say my recognition algorithm makes a mistake, I have that feedback. So how would you set that problem up? Can you, if possible, can you show that?
okay, so I'm not at this point. I'm not sure, very much sure how you do reinforcement learning there, because there you need some action and reward setup. But what I understand is object recognition problem is a supervised learning problem where you have a set of data points.
Hmm. So that is
So
kind of similar in a way that so your value function lies in how good your recognition system is, right? So every time it does a good job, you get a high value, and every time it screws up, it kind of gets a penalty kind of thing. And then uh, there is that neural network which sits.
yes,
So
but
there are.
yes, the thing is why you need reinforcement learning in this setup. So let me understand what object recognition is. So you have a data set XT and YT. So XT is
Mhm,
image of object, and YT
mhm,
is
mhm,
label.
mhm,
So that label can be like whatever the object is, human,
ah,
cat, etc. Now you
ah,
this box is say your neural network, and you are feeding your XT here,
ah,
and you are generating a label. What is
ah,
Y hat T? This is not
ah,
exactly equals to YT. And
ah,
then after feeding all the data, you have a sequence of Y hat T uh,
mm,
from T equals to 1 to tau.
mm,
And you have some loss function. So L
mm,
T, L
mm,
theta. And this YT is, of course, function of the neural network, which is theta.
mm,
And
mm,
loss function is, say, we are using the mean square error. So T equals to 1 to tau YT minus Y hat
mm,
square. Well, so now you take the gradient of the loss and update your theta. So say
mm,
theta n, you update
mm,
theta n plus 1. And you keep on doing that on your data and feed your neural network according to the data.
yeah.
And you have some theta star, which is your neural network. Now you are deploying that in the real system. So theta star is deployed. So this is your you have got from the training, and there is a test. So say there is, I mean, in the real time there are data coming in, and when your data coming in the real time, so you have theta start. So let me write that XTR real data. So there also you're generating the labels Y at
Yeah.
RT.
Yeah.
And yeah, so now you tell me how reinforcement learning is coming into the picture. What is the
Ah,
state? What is the action? What is
ah.
reward?
So the way I'm thinking of it is the state is whatever the weights are. The
Wait,
weights,
okay.
the
Theta is the
current
node.
current parameterization of the neural network is the state. है ना? And whenever it gets something right, obviously it has to get something right. It will not get a reward. But if it does something wrong, let's say it gives you it does not detect a person, or it kind of gives a false alarm. One of those two scenarios, and you have set that is, let's say you get some kind of feedback from the operator when he presses, if he has to press on the screen to indicate that there was a person over there, that is a feedback that it was either not detected or it's some kind of false alarm, right?
Oh,
So if he presses on an existing box, it's a false alarm. If he presses on an empty space, it means that it's a true what is it, false
yeah,
negative.
yeah.
Hmm.
If there is any error, it will be fed back to the
So
system.
now that feedback is available, right? And now I have to update the state. So I have to kind of update learn over there. है ना? So uh, I
Look,
guess it
so
is.
here the fundamental problem is
Hmm,
the uh, state is not being updated by the environment. So in reinforcement learning, the environment should update the state. But what you are saying is whenever I am getting a low reward, I'll update the state. That's not how it works. So,
Okay. I
so
think that so
rather
you can
better, yeah,
you can
rather a
treat
bit,
it you can treat it as a supervised learning problem only, I guess. Keep doing that the above thing.
yes, but rather if you want to fit reinforcement learning problem here, you can think. I'm not sure if it is possible, but what I feel is your current parameter is some sort of policy because that is generating your act and you can treat your generated level as actions. This and inputs as state your this is what is action and what is so from state to action what you employ you employ a policy and that's what your neural network is doing.
Okay. So
It's seeing state
it
and
may got it. So it may operate at one level higher. Let's say I'm controlling the camera now to track continuously, right? Let's say, and that is not doing a good job. Let's say the objects are too fast or too slow or whatnot. Whichever way, my current action control algorithm which I have put over there, whether it's a filter or whatnot, is not doing a good job. It is not able to track a car, let's say when it is very fast, or not able to track a person when there is a group of people or whatnot. So that is a scenario where I can apply the reinforcement learning setup to control the camera itself. How the
okay
camera needs to move to keep tracking the object. You get what I'm saying? So let's say
uh,
by default I've set up the some Kalman filter or something to keep tracking an object, right? But obviously the environment is the environment is not under
changing
control,
okay. Yeah fine. Uh,
right? So environment over here is how the object actually is moving on the ground, right? How fast or how snake-like or how much randomness exists, how much of a Brownian motion is there in that object, right? So that is the environment, and my job is to track the object such that it remains in center of the image all the time.
okay.
That is a better. I think that's a more reinforcement learning kind of setup, no?
Yes you
So
can yeah you can definitely think that as reinforcement learning setup but yes so there uh, I mean whatever the movement of the camera is you have to employ a policy there how the
right.
yeah how the
Right.
camera will move.
Yeah, because what happens is, so when you have a control, what is a hard-coded control algorithm, uh, there is a bunch of noise depending on how the environment is. Meaning, the drone itself is not very steady in that particular climate condition or weather condition. So
Hmm.
that puts additional pressure on the controller. So the controller may not be tuned the best fashion to operate in that scenario, right? But
Hmm.
that is an ideal candidate probably for reinforcement learning, where now your policy will change of controlling the camera with the environment, right?
Yeah, yeah, right.
Okay, got it. Mm. Yeah. So eventually, that is what I wanted to also achieve, and not in just in terms of let's say camera control, but even like a move. So let's say I'm controlling a drone, and the
Hmm.
drone itself is flying in conditions, different conditions all the time, and I have tuned my PID controllers, let's say, to or any kind of controller to like a PID controller, right? And that is not necessarily the best setting in every environmental condition, every wind condition, every altitude, let's say. You know, so I will
Yeah,
set up some kind of a heuristic values right now, but what I really want to do is for that drone to kind of figure it out while it is flying, the best policy. So
okay.
adapt to the environment kind of thing.
Yeah,
So
so
maybe the first, hmm,
yeah, so for that thing, what you have to do, I think you have to search in literature what are the models used for object tracking controller. I mean, you, you know what I mean. So,
Yeah, yeah, yeah.
there must be some models out there,
Mm-hmm.
and I mean, focus on maybe learning algorithm for that particular model. So if the problem is say linear problem, then you need not to look at algorithms which are for nonlinear systems. Right?
Okay, okay. Yeah, yeah.
So,
Makes sense.
for modeling is the first thing to be looked at.
Makes sense. Makes sense.
Okay, so since here I'm stuck, I think I should solve it in theory and then proceed for coding. So what I'll
Okay.
do, I'll solve this and update the notes, and also we'll discuss this in the next tutorial in briefly. And meanwhile, I'll do the coding offline and upload it to the
Okay.
repository.
Okay. Cool.
Okay, yeah. Any more questions?
No, that's it. That's
Oh,
it. Thank.
yeah,
Thank you.
thanks.